Today we are going to discuss about the electronic spectra of ethylene on the basis of group theory. What we see on the screen is a Cartesian system of three coordinates x, y and z. We see the xy plane sigma xy, xz plane sigma xz and yz plane sigma yz. Here we find the structure of ethylene molecule contains two doubly bonded carbon atoms, sp2 hybridized, and so the ethylene molecule is planar on the whole. The x-axis is in the direction containing most number of atoms, that is the direction containing two carbon atoms. C2x is rotation about x-axis through 180 degrees. C2y is a rotation of 180 degrees about y-axis. C2z is a rotation of 180 degrees about z-axis. Sigma xy is the molecular plane, that is all the atoms of the ethylene molecule are placed in this plane. Sigma xz is the vertical plane that is perpendicular to the molecular plane, which cuts through the C double bond C. These two CH bonds are projecting towards us, whereas these two CH bonds are projecting away from us. Sigma yz is the plane that is cutting across the C double bond C, bisecting the C double bond C. You find the two CH bonds on the right side. On the left side of the plane you find the two CH bonds. Now we come to the center of symmetry. There is an imaginary center from which you draw a line. You see the hydrogen atom. If you draw exactly equal length in the opposite direction, you find the hydrogen atom again. Likewise, you find a hydrogen atom here. If you draw a line of equal distance in the opposite direction, you again find a hydrogen atom, and so we have the center of symmetry in the center here. It is the imaginary center. The symmetry operations in ethylene molecule are E, C2z, C2y, C2x, I, sigma xy, sigma xz, and sigma yz. The point group is D2H for ethylene molecule. In our discussion, we are going to focus on the C double bond C alone. It contains a sigma bond and a pi bond. Sigma bond is formed by the head-on overlap of sp2 orbitals over the carbon atom. Pi bond is formed by the lateral overlap of 2p orbitals perpendicular to the molecular plane present in the carbon atom. Now we will apply all the symmetry operations of the D2H point group, namely E, C2z, C2y, C2x, I, sigma xy, sigma xz, and sigma yz over the bonding molecular orbital sigma, anti-bonding molecular orbital sigma star, bonding pi molecular orbital pi, and anti-bonding pi molecular orbital pi star. This is the sigma molecular orbital formed by head-on overlap of two sp2 orbitals. Since it is a bonding molecular orbital, you will find the same signs in both the lobes. Now we will apply all the symmetry operations E, C2z, C2y, C2x, I, sigma xy, sigma xz, and sigma yz to this sigma bonding molecular orbital and see what happens. First we will apply the identity operation. Identity operation is the operation of doing nothing. When you do nothing, the signs are not changed, and so the operation is symmetric, and so the value is 1. Now we will apply C2 Z, that is the rotation of 180 degrees above the axis, and see what happens. This is the Z axis, which is perpendicular to the molecular plane and bisecting the two positive lobes. We rotate through 180 degrees. Signs are not changed, and so the value is 1. Then we come to C2Y, that is a rotation of 180 degrees above the y-axis. The y-axis is present in between the two positive lobes in the molecular plane. And when you rotate through 180 degrees, the signs are unchanged, and so the value is 1. Next we come to C2X. The two lobes of the sigma bonding molecular orbital are present in the x-axis, and so when you rotate through 180 degrees, there is no change in the sign, and so the value is 1. Next we come to the effect of center of symmetry. From the center, when you draw a line towards the carbon atom, you find the positive lobe, and if you draw in a diagonal of equal distance in the opposite direction also, you find a positive lobe, and so signs are unchanged and the value is 1. When you apply the reflection about the sigma xy plane, both the lobes of the sigma bonding molecular orbital are in the xy plane, and so signs will not be changed and the value will be 1. When you do the reflection about the sigma xz plane, that is the plane cutting through the two lobes perpendicular to the molecular plane, and the signs are unchanged, the operation is symmetric, and we get the value as 1. Next we come to reflection about sigma yz. The sigma yz is a plane that cuts the two positive lobes of the sigma molecular orbital. To the right side you find one positive lobe, and to the left side you find another positive lobe, and when you do the reflection they will get interchanged. However, there is no change in the sign, and the operation is symmetric, and you get the value as 1. And if you look at the D2H character table, when you have all values as +1, this corresponds to Ag, and so the symmetry of sigma bonding molecular orbital is Ag. Next we come to antibonding sigma molecular orbital, and we will apply all the symmetry operations of the D2H group to this sigma star molecular orbital, that is antibonding molecular orbital. Only difference is that here you will find one lobe as positive and the other lobe as negative. Compare it with sigma molecular orbital, where you find both the lobes are positive, and when you do the identity operation, the operation of doing nothing, signs are unchanged and the operation is symmetric, and you get the +1. Next we come to C2Z, that is the rotation of 180 degrees about the z-axis as shown here. This is perpendicular to the molecular plane, cutting in between the two lobes, positive and negative lobes, and when you rotate through 180 degrees, the negative lobe will come here, positive lobe will come here, and they are interchanged, and it is antisymmetric, and so the value is -1. When you come to C2Y, there is 180 degree rotation about the y-axis. The C2Y is a rotation about the y-axis, which is present in the molecular plane, cutting in between the two lobes. When you do the 180 degree rotation, the negative lobe comes here, the positive lobe comes here, the lobes are interchanged and the signs are changed, and so we get -1. Next we come to C2X, which is along the x-axis. Both the lobes are present in the same axis, and so for 180 degree rotation there is no change in the sign, and we get +1. When you do the inversion operation, from the center, if you draw a line, you see the negative lobe. If you draw a line of equal distance in the opposite direction, you get the positive lobe, and so the lobes are interchanged and the signs are reversed, and so you get -1. Next we come to sigma xy plane. Sigma xy plane is the molecular plane, Both the lobes are present in this plane, and when you do the reflection, signs are unchanged, and so you get plus 1. Sigma XZ is a plane that is cutting through both the lobes. It is perpendicular to the molecular plane. Upon reflection, there is no change in sign, you will get plus 1. Sigma YZ is a plane that cuts in between the two lobes, positive and negative lobes. And on the right side you find the negative lobe, on the left side you find the positive lobe. Upon reflection, the negative lobe goes to the left side, positive lobe comes to the right side, and so the signs are changed and we get minus 1. If you look at the character table of B2H, you find the same sequence 1, minus 1, minus 1, 1, minus 1, 1, 1, minus 1. Here you find the same sequence 1, minus 1, minus 1, 1, minus 1, 1, and 1 minus 1, corresponding to B3U, and the symmetry of sigma star molecular orbital is B3U. Next we come to the symmetry operations of the D2H point group performed in the pi molecular orbital. Pi molecular orbital contains 2 p orbitals present in the 2 carbon atoms, and this is perpendicular to the molecular plane. 2 lobes present above the plane and 2 lobes present below the plane. And because it is a bonding molecular orbital, you find the same sign lobes, the 2 positive signs present at the top, 2 negative signs present at the bottom. If you apply the operation of E, it is doing nothing, there is no change, and so you get plus 1. When you apply C2Z, there is 180-degree rotation about the Z axis. This is perpendicular molecular plane in between the two 2p orbitals, and upon 180-degree rotation, this positive lobe will come here, this positive lobe will come there, and there is no change in the sign, and you will get plus 1. When you perform the rotation of the y-axis, that is C2y, y-axis in the molecular plane between the 2 carbon atoms, and when you rotate it through 180 degrees, the 2 positive lobes will come to the bottom, 2 negative lobes will come to the top. There is change in the signs, and so you will get minus 1. Next we come to C2x. The x-axis is along the carbon-carbon bond, and when you perform 180-degree rotation about this, the 2 negative lobes at the bottom will come to the top, and 2 positive lobes at the top will come to the bottom, and so there is change in sign, and the operation is anti-symmetric, and we get minus 1. Next we come to the inversion, that is the operation about the center of symmetry. From the imaginary center, if you draw a line in a particular distance, you find a negative lobe, and if you draw a line of equal distance in the opposite direction, you will find a positive lobe. And similarly, here you will find a negative lobe, and when you draw a line in the opposite direction, you will find a positive lobe. And upon inversion, the 2 negative lobes will come to the top, and 2 positive lobes will come to the bottom, and so the signs are changed, and so it is anti-symmetric, you will get minus 1. Next is sigma xy, the reflection about the xy plane. The xy plane is the molecular plane which is shown here. When you reflect, the 2 positive lobes at the top will come to the bottom, and 2 negative lobes at the bottom will come to the top, and signs are changed, and the operation is anti-symmetric, and you will get minus 1. When you do the reflection sigma xz about the xz plane, it cuts through both the lobes perpendicular to the molecular plane. Both the orbitals are present in the plane itself, and so there is no change in sign upon reflection, and so the reflection is symmetric, and you will get plus 1. Next is sigma YZ. It is the reflection about the YZ plane. YZ plane is in between the 2 lobes, perpendicular to the molecular plane. To the right side you find one set of lobes, and to the left side you find another set of lobes, and upon reflection this positive lobe will come to this left side, and this positive lobe will come to the right side. There is no change in the sign, and so the reflection is symmetric, you will get plus 1. If you look at the character table for D2H, we end the same sequence 1 1 followed by 4 minus 1s followed by 2 plus 1, 2 plus 1s, 4 minus 1s followed by 2 plus 1. It corresponds to B1U. So the symmetry of pi bonding molecular orbital is B1U. Next, we are going to look at anti-bonding molecular orbital. The only difference is that in the case of bonding molecular orbital, there are 2 positive lobes at the top, whereas for anti-bonding molecular orbital, there is 1 positive lobe and 1 negative lobe at the top, and 1 negative lobe and 1 positive lobe at the. When you do the operation of doing nothing, there is no change in sign, and it is symmetric, and you get plus 1. And when you do the 180-degree rotation about the z-axis is perpendicular to the molecular plane between the 2 coordinates. Upon rotation through 180 degrees, this positive lobe will come here, this negative lobe will go there. Similarly here, the negative lobe will come here, the positive lobe will go there. And so the signs are changed, the operation is anti-symmetric, and we get minus 1. Next we come to C2Y, that is 180 degree rotation about the y-axis. The y-axis is present in the molecular plane between the 2 2p orbitals, and upon rotation, this positive lobe will come here, and this negative lobe will come there, and there is no change in the signs. And since there is no change in the sign, the operation is symmetric, and we get plus 1. Next we come to C2X, this 180 degree rotation about the x-axis. It cuts through the 2 carbon atoms, and upon 180 degree rotation, the top lobes will come to the bottom lobes will come to the top, and there is change in the sign, and the rotation is anti-symmetric, and we get minus 1. Next we come to center of symmetry, I. If you assume an imaginary center and draw a line in a particular direction, you get a positive lobe. If you draw a line of equal distance in the opposite direction, you will get a positive lobe. Similarly, here you find negative lobe, the opposite direction you find a negative lobe. Upon inversion, there is no change in the sign, and the operation is symmetric, you will get plus 1. Next, we come to the reflection about the xy plane, sigma xy. Xy plane is the molecular plane shown here. There are 2 lobes above it and 2 lobes below it. Upon reflection, the 2 lobes above it will come to the bottom, and 2 lobes below it will come to the top. Negative will come to the bottom, positive will come to the top, and there is change in signs, and the operation is antisymmetric, and we get minus 1. Next, when you do the reflection sigma xz, there is a reflection about xz plane. Xz plane passes through both the lobes. Both the 2p orbitals are contained in the xz plane, and so there will not be any change in sign, and the operation is symmetric, you will get plus 1. Next we come to the reflection sigma yz about the yz plane. Yz plane is in between the 2 2p orbitals, cutting through the CC bond. On to the right side, on the top you find a negative lobe. To the left side, on the top you will find a positive lobe. Upon reflection, the positive lobe will come to the right, negative lobe will come to the left, and the signs will be changed, and the operation is antisymmetric, you will get minus 1. If you look at the D2H character table, you will find the same sequence, 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. Here also 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. This corresponds to B2G. So the symmetry of pi star anti-bonding pi molecular orbital is B2G. Having found out the effect of the symmetry operations of D2H point group on the sigma bonding molecular orbital, sigma star anti-bonding molecular orbital, pi bonding molecular orbital, and pi star anti-bonding molecular orbital, we will summarize what we have found out like this. The symmetry of sigma molecular orbital, that is bonding molecular orbital, is Ag. Sigma star anti-bonding molecular orbital is B3U. The symmetry of pi bonding molecular orbital is B1U. The symmetry of pi star antibonding molecular orbital is B2G. Now we look at the ground state configuration. We consider only the C double bond C. It contains sigma bond and pi bond. Sigma bond contains 2 electrons and pi bond contains 2 electrons. Now the symmetry of sigma is Ag. So substitutes Ag instead of sigma. And the symmetry of pi is B1U and substitute B1U instead of pi. And now look at the character table. Ag is all positive and you square it, it's once again Ag, all positive ones. And B1U contains positive as well as negative values, but when you square B1U, all the negative numbers will become positive. And so all will become positive, it will correspond to Ag. The product of it is Ag, and so symmetry of ground state configuration is Ag. Now we will come to pi to pi star excited state, that is, one electron in the pi molecular orbital will be moved to the pi star, and so the remaining electron will be in the pi and one electron has moved to the pi star antibonding molecular orbital. Now the symmetry of sigma is Ag, the symmetry of pi is B1U, and so instead of pi is substitute B1U. Symmetry of pi star is B2G, instead of pi star is substitute B2G. Now look at the character table. Ag is all positive, when we square it, it's once again Ag. And we have to take the direct product of B1U and B2G. 1 into 1 is 1, minus 1 into 1 is minus 1, 1 into minus 1 is minus 1, minus 1 into minus 1 is plus 1, 1 into minus 1 is minus 1, minus 1 into minus 1 is plus 1, 1 into plus 1 is plus 1, minus 1 into plus 1 is minus 1. So if you take the direct product of B2G and B1U, you will get B3U. And Ag is all positive, and when you take the product, you get the result as B3U, and this is the symmetry of pi to pi star excited state. Now we come to sigma star excited state. Out of 2 electrons present in the ground state in the sigma orbital, 1 electron moves to sigma star, that is anti-bonding sigma orbital. Now for sigma the symmetry is Ag, for pi the symmetry is B1U, for the sigma star the symmetry is P3U. And if you look at the character table, Ag is all positive. This is the B1U, and when you square the characters of B1U, all the negative characters will become positive and we get the result as Ag. B3U contains plus 1 as well as minus 1, but we don't square because there is only 1 electron present in. The result of this product is B3U because Ag is all characters positive. So the symmetry of sigma to sigma star excited state is B3U. Next we come to sigma to pi star excited state. Out of 2 electrons in the ground state in sigma orbital, 1 electron moves to pi star orbital. The other 2 electrons in the pi orbital remain intact. The symmetry of sigma orbital is Ag. Substitute Ag for sigma. There is only 1 electron here. The symmetry of pi molecular orbital is B1U. Instead of pi B1U, we have B1U square. The symmetry of pi star molecular orbital is B2G. Instead of pi star, substitute B2G. And look at the character table. Ag is all positive. B1U contains positive as well as negative characters, but when you square B1U, all the characters become positive, and so you get Ag. B2G contains plus as well as minus characters. And if you take the product, you get it as B2G because Ag is all the characters remaining positive. So So the symmetry of sigma to pi star excitator state is V2G. Now we have to find out which of the transitions are allowed, which of the transitions are forbidden, that is not allowed. For this, the dipole moment vectors x, y, z is found against the corresponding irreducible representation in the character table. The transition is allowed. If x, y, z is not found, the transition is forbidden, not allowed. We are referring to x power 1, y power 1 and z power 1 and not a square, y square, z square, not xy, xz, yz, etc. Now we'll go to pi star excitator state. We have to take the direct product of the ground state and excitator state. The symmetry of ground state is Ag. So instead of ground state you find this substitute Ag. Excitator state for pi star is B3U. So here we substitute B3U. Ag is all positive and so the result is B3U. And if you look at the character table against B3U irreducible representation, you find the Cartesian coordinate x and so the transition is allowed. The pi star transition is allowed. Next we come to sigma star excitator state. Again you have to take the direct product of ground state and excitator state. Ground state is Ag and for sigma star the excitator state is B3U. So substitute B3U here. Ag is all positive characters. And when you multiply you get B3U once again. Look at the character table against B3U. You find x power 1, that is x. And since x is found, the sigma star transition is allowed. Next we come to sigma to pi star excitator state. Take the direct product of ground state and excitator state. Ground state is Ag and the sigma to pi star excitator state is B2G. Here we substitute B2G. Ag is all positive characters. And if you take the product, it's once again B2G. And look at the character table. Against B2G, you find xz, but you don't find x or z. And since you don't find x, y or z, sigma to pi star transition is not allowed. If we summarize all the results we have, we find that the pi to pi star transition is allowed. Sigma to sigma star transition is also allowed. But the energy gap is very high. We find the sigma here, find the sigma star here. The energy gap is very large and so this will not happen normally. Sigma to pi star transition is not allowed. So the predominant transition will be pi to pi star. Thank you.